for research. And once people start posing questions, other people will start replying, and hopefully we'll get a nice thing going. Brian will moderate it with the help of Akshay and sound.
Sound?
So, okay.
Oh, there you are.
We're just sitting quietly, hoping we wouldn't see you. We'll be running around with the mics, but don't wait for the mic. We want to keep the dialogue flowing, so you can just speak loudly, and if you need a mic, we'll get it to you. And we need a couple of note takers. I noticed a whole bunch of younger people there teching in real time. Everybody's looking at this guy here. No, your job is quite simple. We need two of them, so it's going to be you, and it's going to be. Are you good at teching? Okay.
So we have two volunteers. Do you know who they are?
The two volunteers are this guy and that guy.
Okay. Well, you have to get the notes from them afterwards, right?
And your job is just to transcribe what's on the board. So the real note takers will be here in the front writing down, and you just have to accurately write down what they do.
And maybe comments too.
Okay.
Okay. Go sit down.
Okay. So let's get started.
Okay. So I'm Brian Connery from AIM, and AIM is one of the sponsors of this, and we're very happy to help sponsor the birthday conference for Peter. He's been involved with AIM for a long time, is the chair of our board, et cetera. And at AIM, we do these moderated problem sessions, and so that was a condition for AIM giving money to AIM, was that we would have a moderated problem session, but I figured there'd be like 25 or 30 people here. I had no idea Peter knew so many people. So I don't know what we're going to do with this whole group, but like Mike said, let's try to keep it, we'll keep it lively, so you don't have to really, you can just, it's a discussion, right? So if somebody poses a problem and somebody wants to say something about it, they should just do that. And if you're not audible, a microphone will appear in front of your face momentarily, and you can talk into that. All right. Now, I don't know if we should try to restrict. Number theory is a big subject. In some ways, it's getting closer together, I think, as time goes on. But are we all going to be able to understand the questions that we all ask? Well, we'll see. So who wants to start? Yes, Matt.
So this is a question about talks that will come later in the conference. But it's known, for example, that if you look at a tower of Bianchi groups, say of increasing level, and you look at the Betty numbers, that they go sublinearly in the volume. So less than the volume. And so one question I think is an interesting question, and as far as I know is open, is if you look at the FP Betty numbers. So growth of FP Betty numbers in situations where the real Betty number is known to grow sublinearly, can you prove that the FP Betty numbers grow sublinearly?
Sublinearly, is that what you said? Yeah.
Even like little o of the volume. A power will be great, but little o of the volume would already be, I think, is unknown. And so just one comment on this question is my understanding is that if you look at does the total torsion in cohomology, and you maybe take the log of the size, that should go like the volume in the Bianchi case. I think that's results in conjectures of Akshay and Bergeron. But here we're kind of taking the FP Betty number, so it's kind of like you fix a prime P and you're looking at the P part of that torsion. And so that should be like little o of the volume. So somehow the Bergeron-Venkatesh result should be, in some sense, that growth should be being caused by large sporadic primes appearing rather than a systematic choice of prime. But anyway, Akshay probably knows more about that than I do.
Anybody have any comments on that?
Yeah, I think Lobotsky.
Okay, where is Lobotsky?
That's a good way to assess a guy. Yeah, he's thought of it. Now there's a problem, say, for it also seems not just looking at class groups of, say, imaginary quadratic fields. Can you prove that class groups of imaginary quadratic fields are not all 5 torsion? Are not all what?
5 torsion.
No, is somehow not, is like less than delta to the half minus the explicit number. Can you prove that? And that's a sort of analogous question. If you know the growth of the entire class group of measuring magnetic fields, can you prove backstop the P part of it? We will do one.
So Hassan will get this one, okay? Give him 30 seconds here.
The analog for class group? A rough analog, I would say.
You certainly have big chalk here in Princeton.
Okay, so you want to prove that there are elements in the class group that are not, well, just to kind of give, I mean, okay, let me know it's not very precise, but give good balance in the P part. Non-trivial balance. Yeah, I did fine.
So how hard are these questions? Are they like thesis topics or dinner topic? What?
I don't know, I think it's seems quite hard, but I think quite interesting. But I mean, maybe the philosophy with Francesco's question too is that, again, you have some growth, you have this sort of systematic growth of the class number, but the idea is it should be being caused by sporadic large primes rather than by kind of a fixed small prime appearing. So that's kind of the linking philosophy between the two questions.
So on GRA, you could say something because you will be able to construct a large, so you'll be able to construct primes which are very small, let's say split. That would be, their order would not be exactly P. Is that like delta to the epsilon or delta to the half minus constant? So it could give you delta to the half minus some constant which is half minus one. So one array can say something.
Like even on our, it would be interesting to say something approaching the truth.
It would not be something, so truth should be presumably P3 or constant to the epsilon. And you should be able to get something like e to the half minus one. Maybe I should put this in quotes. Something like that should be.
Lillian? Your name was just mentioned.
So we prove non-trivial bounds, upper bounds for averages and higher moments of the P part for P being 3 and above. Whereas, of course, the average with P equals 3 is not improved because that's non-optimal already. But the average is improved for 5 and above, and the second moment and a higher moment will improve for 3 and above.
Okay, but it doesn't say anything for the element really long. It does say something long.
Okay, another question?
I have a question then. This is a perfectly doable project. Would be good, for somebody who's young and good with computers. It's been a number of years since Elke's rank 28 record, and also the Watkin Elke's rank records with relatively small conductor. And can somebody out there, beat that? How high a rank can one find by example? And the ones with the relatively small conductor would give us a little bit of insight as to the rate of growth of the conductor relative to the rank. So that's just a challenge, and I see no reason why the those records should stay for all time.
Are people working on that right now?
Not to my knowledge. I mean, everyone assumes that if Elke's, got a big number, no one's going to beat him. But it's been like, 20 years, or I don't know how many years since rank 28. But
So the computer's better.
okay, feels like.
Even the family rank is 18, which LP had, and Shiora has like 68. And it's possible that specializations you can get some, and that will give some evidence to this Poonen and so on. They are thinking that 28 is the best. So it's, I think, a very good problem.
So, yeah, so can that just be repeated? So there are people who believe the rank is bounded, but those people, what do they believe the bound is?
I think you were saying 28. Okay, so how many people here think the rank is bounded?
Maybe.
How many think it's unbounded? And how many abstained?
And there was a second part, not just rank 28, but
Something in families? No.
But Watkins and Elkes have a paper where they find the first examples of rank up to 11, and with small conductor, small might be but small relative to the rank. So can one extend those tables, because those tables really give a clue as to at what conductor does one start to see a certain rank. So is it growing like log n over log n, or square root log n times some other small factor?
So they don't actually prove that it's the smallest ones, right? Or do they?
No, but they have they give
Pretty small, reasonably small.
heuristic reasons for expecting them to be.
Okay, and so somebody has to write that down, right?
So just write it
So
as
the question was,
extend the Elkes-Watkins
Find low
minimal
conduct-
conductor
small
table.
minimal conductors.
You have only 28 examples, right? So what
Right.
does it mean?
No. There's a gap up to 20. No one has found ranked. In between there's a lot, and what distinguishes their table is that they believe they found the examples with close to the smallest conductor allowed. Like the rank 28 example is far from being the optimal one, meaning with smallest conductor. Sorry?
Do you know this?
Yes, I know it, but I can't prove it. And the way you know it, I could tell you why. I could give you my one reason is you just look at the APs. In all of the examples in the Elkes-Watkins table, the first few APs are right up against the Hasse bound. You draw the parabola, and you just see them. They're trying as hard as possible to be as negative as possible. In the rank 28 example, you're seeing more like the Sato-Tate distribution right away. So.
Yeah, just to maybe give more motivation, I agree entirely with Michael. Beating 28 might be hard, but getting lower conductors for ranks below 28 is definitely doable. Somebody will be able to do that.
Okay, something else.
We have a question in the front.
Oh, sorry, Frank.
This is a question about thin groups, which we'll also hear about. So suppose you have a subgroup of SL3Z, then, and which is risky dense. Then I forget who proved this theorem, that basically this group, it sees all the finite quotients. Not the congruent subgroup property, but right. But it sees basically all the finite quotients of SL3Z. On the other hand, if it has some quotients that are not congruent quotients, then it's not a congruent subgroup. So the question is that an equivalent statement to being a thin subgroup? So in other words, if you have a thin subgroup, does it necessarily have a finite quotient? No, but they might have quotients that are not congruent subgroups. So certainly all the quotients of SL3 basically come from the thin subgroup, but
does a thin subgroup necessarily have a finite quotient? I'm just asking. You could compute some examples. Which is not coming via the map to SL3Z. So in other words, is the congruence, is the finite completion of the group basically the finite completion of SL3Z? I have no idea, but I mean, that's one way to possibly prove a group is thin, for example, is to prove it maps onto like A17 or something. But is that always a method by, could that be a way of always proving, you know, if you have a thin group? Sure. So it's not a question of I mean, gamma will basically see all the finite quotients of SL3Z, but it might have extra finite quotients. So that's the question. If it's thin. So the question is. That's finite group, yeah.
There's a great theorem of Winberg, which is quite useful in showing groups are thin, which is if you take a rational quadratic form in 30 or more variables, and you look at, can you write? Akshay, maybe just write a few things here. So F a rational
quadratic form in 30 or more variables.
Well, all right, F a rational quadratic form, G the orthogonal group of F, and GZ or OFZ the integral orthogonal group. And then if you take, I'm just describing first the theorem of Winberg. And GZ. Okay, now take the subgroup generated by hyperbolic reflections sitting inside OFZ. Let's call it R sub 2. Then he shows that Winberg's amazing theorem is that that's a normal subgroup, so GZ divided by GZ divided by R2 is infinite if the number of variables is bigger than 30. 30 or 13? 30. Nicolin has worked out all the exceptions in small dimension. Okay, the question is Winberg's theorem true if you allow also reflections which are Cartanian involutions? So a hyperbolic reflection will be one who's a vector coming from a root vector of length plus or minus 2. The 2 gives a hyperbolic reflection. The other sign will give a Cartanian involution. So if you take the full Weil group, is Winberg's theorem still true? All reflections. That would be a very powerful way to show groups thin, like hypergeometric groups whose Zariski closure is orthogonal. So is there a generalization of Winberg? And Chen Meiri has shown that something quite interesting there, just by the way, that GZ over R2 is always non-amenable if the dimension's bigger than 90. So it's not only infinite, but it's non-amenable, just as a matter of interest. So the question is to extend Winberg's theory not just on hyperbolic reflections, but elements of order 2 which come from root vectors of length minus 2 rather than plus 2. That would be extremely useful. And I think that theorem is doable.
Any comments?
Lubotski just walked. No, it's not it.
It looks like Alex. Alex, do you have any questions? We're doing a problem session.
Alex,
Do you want anything you want us to solve?
the first question. Do you have any insight about the F2 or FP, what did he ask there? FP Betty number, growth rate.
See what happens when you arrive late. Faculty this question. Can you write down any presentations of this
No,
subgroup in some sense? Or at least to think about it.
so Winberg's theory is a generalization of Coxeter's theory of that a fundamental domain for a group generated by reflections, the walls, the fixed set of each reflection defines the fundamental domain. So Winberg's theory is based, the fact that he can prove that's always infinite, or the fundamental domain's actually got infinite many sides once the dimension is large, is based on canonical fundamental domain that you can compute for R2.
So then he can write basically a presentation.
He can for R2,
Yeah.
but if the opposite sign, I don't know how to do it.
Well, I would just be curious, if you have a presentation for R2,
Yeah.
you can start to look at this like that. You can start to compute the question on the right as well.
Yeah.
Because you know it's
In practice, yeah, so
like what's the
Meiri, Fuchs, and I do have a theorem which goes halfway towards proving that, but it would be much better if it were just a general theorem. Right.
I'd like to ask what's the profinite?
Yes, yes.
allowed?
Yeah. Yeah, this you can answer. The R2, the quotient group, R2 is generated by reflections, and you look at the group generated by that. The quotient group you can't compute in principle, as it's usually a free product of various kind of groups. Borcherds has computed it, probably the most interesting. Conway also was the first to compute one such example. Signature 25-1, connected to the Leach lattice.
Alex, last chance. Okay, somebody else have a question? Okay.
So this is a general question about central values of all functions of GLn plus GLn minus VLR. So let's simplify. Let's say it's over Q, and we're looking at cluster representations that are self-moving. Fixed representation of GLn, I, GLn plus GLR, R less than n, and fixed pi over GLn, and look for pi prime such that the central value of all self-moving L of pi plus pi prime 1/2 is not equal to 0. So that's it. So now, the question is going to come to the end. For pi plus
Pi times pi prime.
pi plus pi prime, not 0 and
For some pi prime.
For some or for all?
fine, yes,
For some. For some.
and self-dual. So for r equals n minus 1, this is often possible. For r equals 1, like other character Peter said, it told me 2 years ago that he thinks it's more difficult than Riemann.
It-
Is pairs n and r, is this more difficult than Riemann?
I think that's a misquote. I mean, it is known for some range.
What?
For n equals 2 and r
No,
equals
for n equals, yes, well, for n equals,
n equals 3, you can also do so there are some ranges in which you can do it, but small ones. And you can always get non-vanishing slightly to the right.
Slightly to the right.
Yeah. Yeah, I think it's a very good question, because I think what's missing here is a proper innovation of the analytic machinery of the trace formula higher up. And I'm sure that you would, so right now, Arthur hasn't written the trace formula down for you. Nobody, is that, I mean, it's the only trace formula that's used for GLN is if Arthur wrote it down, right? What I mean is to make the, I think there's a very important question here, and that's to make the analysis of the trace formula flexible as it is in GL2 for GLN. With these kind of problems in the back, these should come out once you have a sufficiently flexible version. Right now, the only, maybe Mueller will talk about it a little bit, but the only versions are what people take out of Arthur, and it's not analytically flexible, which is what this question is. In other words, the standard attack on this problem is what's called the approximate functional equation. You then have to average over these twists. And then you have to write out some sufficiently flexible trace formula in order to execute that.
So this kind of problem would drive the development of.
Yeah, there are simpler problems, but I think that that's one of the central issues in the subject is, so to speak, GL1 was developed nicely in the 70s, GL2 in the 80s till now maybe, but we've never really developed a theory analytically. And there's always a dream that when n gets large, something improves rather than gets worse.
So I misrepresented what you told me to do.
I think I don't think I said that.
Well, so what simpler problem would you suggest that would also
Zeros,
no line zero, one level density
one
of
level densities, those you can, because there the aim is self-fulfilling, in that you say the support of a Fourier transform is whatever you get.
whatever you get, right?
So
However far you can
You will
go.
always get somewhere.
Right.
Exactly. But I think all these are just practice problems for those. That has applications. That's why he's asking it. So it's an important issue. Unless you come with a different method, which might be related to periods or some. There may be other methods. In fact, Volz-Berger's theorem proves it for GL2 twisted by quadratic without
That's very special.
Yeah, that's good.
You place some restrictions on it, you could try to do the Friedberg-Jacquet theory higher order. So if you wanted to show non-vanishing.
Right. I think certainly the multiple Dirichlet series method, that's what it's good for, not so much for subconvexity, but for non.
This is GLN plus GLN inside GL2. So you can get something like this.
Okay, so we are talking about developing a trace formula analytic. It's important.
Your comment was on R equals n.
As an example of some place where you might try to do this, look at GLN cross GLN inside GL2N. So let me just say, okay, let me compare work of Friedberg and Jacquet. Yeah. I think this is a really nice period info that's directly related to that central value times the core of the adjoint.
Any relative trace formula which brings out the special value you might be able to prove there's some twist by, because if all of them are zero, then you get some functional which is identically zero as you vary over all pi primes, and that might already be just too much. And there's some, because that might span quite a lot
So in your question, n and pi and r are all fixed, and you're trying to find pi prime.
One of many questions that
Sure.
could be anti-economic twists, in the case of GL1, so it wouldn't be subgroup in this case.
Yeah. You go ahead, you and then Nick next. Yeah, go ahead.
Bottom about whether a thin Zariski-dense subgroup SLZ must have a finite quotient which is not a quotient of SL3Z. Assume it does not, then it really means that the profinite topology of SLZ induces the profinite topology of gamma, in which case one can prove superrigidity for gamma, namely one can use fairly standard technique to show that every representation of gamma can be extended to SL3Z, and therefore, because of superrigidity of SL3Z, can be extended to SL3C. And so, an almost, not really equivalent, but a very related question is whether SL3Z as a thin subgroup with the superrigidity property. And that's one of a sequence of questions that one can and should ask whether thin arithmetic groups can share some of the very strong properties of arithmetic groups. For example, we don't know if SL3Z as a thin subgroup with Kashdam property T. This is, for example, completely open. Regarding superrigidity, there is an interesting example in arithmetic groups. In a product of two rank 1 groups, you can construct a superrigid group of which is thin. But in SLNZ, this is completely open. Anyway, so this is a first of many questions of this type, that all of them are. What we really need is new sources of thin groups which are not free or not surface group, but something which are really complicated somehow. So,
Alex, do you have an opinion on what the answer to your question is?
What?
Do you have an opinion on what the answer to your question is?
I don't know. I think what makes it so interesting is that it's even difficult to guess. I don't know. If I have to bet, I will say that in SL3Z, if you insist on SL3, then maybe the answer is that we will not find. Namely, that every subgroup there will have a quotient which is not in SL3Z. But if you will go to SLNZ, then I think that eventually, at the end of the day, we will have some super rigid subgroup of SLNZ which are thin. But this is just a wild guess.
Nick?
So there are known examples of thin subgroups of SP4 and lots of odd orthogonal groups. But there are local systems, sort of mature in nature, that have this monodromy groups, various exceptional groups. So, for instance, G2. And as far as I know, no one's worked out whether in any of those examples the actual group is thin or not. I think it would be interesting to know the answer.
So, what's your simplest example of G2 family?
It's inside a family of elliptic surface. But it's very concrete.
Yeah. So I could take the rigid local systems with group G2 have.
You don't even have to be rigid.
Okay.
I mean,
Is the
answer no in that case? What? Is the answer no in the rigid case?
The answer is unknown in all cases.
Do you have any guesses?
I mean, the groups that you compute might well be thin, for example.
I can't guess.
The question could just simply be, in any of your examples, determine if the group is arithmetic or thin.
One could certainly pose that question. You're already the same question in terms of coming from monodromy. Do we even know for SLN? SLNZ? I don't think so. I mean, Steve Humphreys has these examples with thin subgroups of SLNZ generated by unified pseudo-reflections that are due as but it's not at all clear that they can be realized in some other system of, so to speak, algebraically microcarbon.
Does it make any difference to geometry if there's thinner?
Does it make what?
Does it make any difference to geometry? Is there any sort of algebraic or geometric consequence which is different?
To the extent that the reason people like me are interested in this stuff is for equidistribution questions in finite characteristic, we can't tell if it's thin or not. And to the extent that we, so to speak, don't care in terms of applying it, it's maybe the anthropomorphic fallacy. We do what we can and we ignore what we can. But now, thinness does not seem to have, right now, observable consequences in that world.
There are examples of families of RDL that happen in the detail that Peter knows, where Savage made this computation. But there's a connection between thinness and some Lyapunov exponents or something in there.
I think actually Erskine was the first to note it. Is he here? I don't think he's coming in this evening. Yeah, there are 14 Calabi hours with hypergeometric SP4. 7 are thin and 7 are arithmetic. And Erskine and Konsevich have observed that the rationality of some Lyapunov exponent associated with variation of Hodge structures is determined by this breakup. And Konsevich has some wild guesses which he since has told me he has no understanding. But I think when Erskine's here, he's the guy who first observed this dichotomy between these. So your question was, what's the geometric meaning? He pointed out that this 7 and that 7 have a dynamical difference in what they do with this Zorich and Savage cosine. Some Lyapunov exponent associated with it, which does seem to go exactly with the 2 7s. The analysis of the 2 7s as it exists now is purely group theory. The way it's resolved, with no geometry. Some of us are very interested if you're going to sieve. Let me answer that question. If you're sieving on a thin group because it came your way, and you know that it's, so this is a case where I really do want to know whether the group's arithmetic or not, because I can apply a strong approximation if it's arithmetic. All the local to global principles are then standard ones in algebraic groups, while if the group's thin, then, then it's a much more difficult problem. So there are some of us who are very interested in the distinction.
All right. I think we have time for one more question.
Now it has to be about a zero.
All right, Henrik.
Ask Henrik, what's the most striking thing you can do with the existence of a Ziegel zero?
Yeah, I think it's a question for you, yeah. What? Cry. That's striking, yeah.
By the way, I don't know what a Z equals 0 is.